In this video, we'll attempt to answer this question, what is a laser? But I want to start with a warning that I'll just read here. A full explanation of a laser is beyond this class. This video will teach you quite a bit about lasers, but not everything. Now, if you recall, an EM wave actually has two transverse waves in it, an electric wave and a magnetic wave. In this picture, the electric wave is in red, going down this way. The magnetic field comes out of the page at you. They happen to be at 90 degrees to each other. Now, most light you'll see, the, um, the light waves are oriented in different directions. Now, I've represented one wave here, red up, that's the electric, and the blue sideways, and that's one wave. In say a flashlight, you'd have millions of those waves, and they'd be oriented all the way around the map. So this one here, you see one here that's just like that one, but then next to it, you have one that's kind of curved. It's spun around a bit. Say this one here, or maybe this one here. Can you see they're spun around? They're coming from all different angles. And this light's coming out of the page at you. If you were to see a flashlight right in your eye right now. And you see things are spread out in all different directions. Well, with a laser, they're not done that way. They're all in the same orientation. I've chosen up and horizontal. There might be another one, but they're all together. See? They're all kind of piled on top of each other in the same orientation. And that helps make the light of a laser much more powerful. These individual rays or waves build on each other. The video code here is EM lasers, electromagnetic lasers. Now also, most light, say from a flashlight, is, we call it out of phase. What does that mean? Here's a crest here, right? If you go down this line to the next one, the crest is not beneath it, is it? In fact, a trough pretty much is. Right there, those two would pretty much cancel each other, wouldn't they? This is different, and that's different too, okay? But they're not synced up. It says here, since they're out of sync, they tend to cancel each other out. We see a great cancellation right here. So that limits the strength and power and energy of a regular light, say from a flashlight. In a laser, though, through technology would make them all be in sync, in phase. So all the crests are together, all the troughs are together. And this makes for a very powerful wave. Think of it this way. Let's say you had waves in the ocean, and say they were all 3 feet high, and you could put on top of one wave another one 3 foot high, and oriented like this in phase. So the crests are always there, with the troughs are always together. Then another one, say a million of them. You'd have a gigantic high wave, wouldn't you? Yes, that's what putting these things in phase does for the EM waves inside of a laser. Now, almost all lasers use one of the colors from the visible spectrum. Remember Roy G. Biv? Red, orange, yellow, green, blue, indigo, violet. Most lasers use one of these colors. Red and green happen to be the most common, although I've seen blue as well. Now, it's funny, after all this, really the most important message here, and especially for the MCAS, is this. Lasers are electromagnetic waves, usually visible light. They're just manipulated to be of high energy. A couple things are done to them. But they're still EM waves, aren't they? They're probably light waves, visible light. So when you encounter the word laser in the MCAS, you should treat it in large part like a regular EM wave. For instance, does a laser need a medium? No, a laser is an EM wave. It does not need a medium. Does it go at the same speed as all other EM waves? Yes, it does. Okay, it's just a regular EM wave that's been adjusted in a couple ways to be higher energy. The point is they are EM waves. Treat them that way on the test. Bye.